Okay, let's continue on the applications of differentiation. In this particular section, we're going to learn how to sketch a graph. So also I'm going to go over the summary of the curve sketching skills. Summary of curve sketching skills. We're going to objectives. Throughout the whole section, we will learn how to analyze and sketch the graph of a function. Analyzing the graph of a function through the first, using first derivative and second derivative. So anytime when you try to sketch a graph of function, either using a graphing calculator like a TI 83, 84, 89, and 92, or in this course you'll learn Maple, right? If you graph using Maple, is most of the time you have to determine how wide you want to see the graph, meaning you want to see the whole picture of the graph or just a particular portion of the graph, and that's kind of important. And you can manipulate that by restricting the domain range. Let's take a look at this example, right? For example, this function is f of x equals to x cubed minus 25x squared plus 704x minus 20, and this is a third degree polynomial function, right? If you look at these two graphs, graph number 1 and graph number 2, they look very different, right? And you wouldn't think they refer to the same function, right? But in this case, this is just two different viewing windows for the graph of the same function. F of x equals x cubed minus 25x squared plus 74x minus 20. So the same graph. However, if you look at the first graph, the domain is just from -2 to 5, and then range just from the -10 to 40. And if you look at the second graph, the domain is from -10 to 30, and range is from -1200 to 200. So as you can see, right, the second graph covers a much wider range of the function. That's why they look so different. So when you graph it, just depends on your needs, right, or the specific requirements. You probably want to graph the function in a certain way. I want to make you understand how this affect the result of the graph. So now, after this example, you understand that it's very easy to get a completely different view of the graph referring to the same function. So this is kind of a very easy to achieve. So now let's take a look at how we analyze the graph of function. Some guidelines to determine a good view window of a graph of function. First one, determine the domain and range of the function. So domain is all possible x values, range is all possible y values. And second step, determine the intercepts, meaning x-intercept, and y-intercept. Asymptote, the two type of asymptote, horizontal asymptote and the vertical asymptote. And also the symmetry of the graph, if any, right? And the third step, locate the x values for which f prime of x, which is the first derivative, and second derivative f double prime of x, either are 0 or does not exist. And the critical number comes from the first derivative. So if you set f prime of x equal to 0, you find the critical numbers. And if you set f double prime of x equals 0, you'll find a possible point of infraction. Okay, let's take a look at this example, sketching a graph of rational function. Analyzing and sketching a graph of f of x equals to 2x squared minus 9. That's numerator over denominator, which is x squared minus 4. So first thing, let's find the first derivative. So in this case, we're going to use the quotient rule. So the quotient rule u is 2x squared minus 9. So the u prime is equal to 2 times 2x, right? So which is 4x. V equals to x squared minus 4. V prime is 2x. Okay, so using the quotient rule, so in that case, f prime of x equals to u prime, which is 4x times v x squared minus 4 minus u 2 times x squared minus 9 times v prime which is 2x over v squared. So that's going to be x squared minus 4 parentheses squared. Then once you expand it, you're going to get 4x cubed minus 16x minus 4x cubed plus 36x over x squared minus 4 squared. Now after you cancel 4x cubed here, 36x minus 16x will end up with 20x, and denominator being the same, x squared minus 4 squared. Alright, so that's the first derivative. And second derivative is based on the first derivative. So now u is equal to 20x. So the u prime is just 20. V is x squared minus 4 parentheses squared v prime. So you gotta use the power rule first, 2x squared minus 4, and then we take the derivative of the inner function x squared minus 4 prime. So it's 2x squared minus 4 times 2x. So that turned out to be 4x x squared minus 4. So that is 4x cubed minus 12x. Right. Now after that, we're going to put together the f double prime. Because u prime is 20 times v is x squared minus 4 squared minus uv prime 20x times v prime, that's 4x cubed minus 12x divided by v square, so it's x square minus 4 square square, and make it to the fourth. Okay. So now let's take a look at simplify this. After you simplify this, you will end up with, let's see, so 20 x squared minus 4. If you look at it, this thing is equal to that. So every single term, right, in your numerator denominator has x squared minus 4. So that means you can reduce every single term in your numerator denominator by x squared minus 4. That will give us negative 20x then times 4x over x squared minus 4 to the third. So after you finish simplify this, you'll end up with 20x squared minus 80 minus 80x squared. 20x squared minus 80x squared, that's negative 60x squared. And LCD here will become negative 20, right? And 3x squared plus 4. Okay, that becomes the numerator, and x squared minus 4 cubed. That's the denominator, so that's why it matches with the outcome here. And in terms of finding the x-intercept, first step, first derivative, second step, second derivative, third step, find the x-intercept by setting f of x equals 0. That means 2x squared minus 9 over x squared minus 4 equals 0. So 2x squared minus 9 equals 0. You can turn into proportion cross multiplying, end up with that. So x squared minus 9 equals 0. X squared equals 9, x equals plus minus 3. Okay, so x-intercept will be negative 3 comma 0 and 3 comma 0. Okay, check that. Y-intercept is setting x equals 0. So f of 0 becomes 2 0 squared minus 9 over 0 squared minus 4. So that will turn into negative 18 over negative 4. So that becomes now 2. Now that's why y-intercept is 0 comma now 2. Okay, so that's a full step. And the next, fifth thing is the vertical asymptote. So you set in the denominator equals 0, right? And you find vertical asymptote meaning setting x squared minus 4 equals 0. So x squared equals to 4. In that case, x equals to plus minus 2. So the vertical asymptote is x equals negative 2 and x equals 2. 6 will be the horizontal asymptote. Remember, when you take the pre-calculus class, horizontal asymptote, in this case, numerator denominator has the same power. So take the leading term in the numerator, divide by leading term by the denominator. So horizontal asymptote equals to equals to 2x squared over x squared. And all leading to the numerator denominator. I cancel x squared becomes 2. So y equals 2 is the horizontal asymptote. Critical numbers, use 7 steps to find the critical numbers. You go back to the first derivative and setting first derivative equals 0. Yeah. Setting f prime of x equals 0, which means 20x over x squared minus 4 squared equals 0. That means 20x equals 0, x equals 0. Okay. So that's why the critical number is x equals 0. Eighth step is find a possible point in fraction. So you set in second derivative equals 0. However, negative 23x squared plus 4 over x squared minus 43rd. When you set this equals 0, numerator will never equal 0 because 3x squared plus 4 is always going to be greater or equal to 4. So there's no possible way for that to be 0. Never equal to 0, right? That means no solution. So indicates there's no possible point of fraction. In terms of domains, all real numbers except whatever number make the denominator equal 0. In this case, plus minus 2 make the denominator equal 0. We also calculated here. So, right. So all real numbers except x equals to plus minus 2. You can also use interval notation. So it's going to be from negative infinity to negative 2, union, negative 2 to 2, union, 2 to positive infinity. Yeah. And that's the domain. Alright, symmetry. As you can see, it's an even function, right? Because both exponents on top and bottom are even power. That means it's an even function. That's why the symmetry is for even function. The symmetry is symmetric with respect to y-axis. As you can see, right? You place x with negative x. The y value is the same. So, same y value. So that's why it's symmetric with respect to y-axis. Right? X becomes negative x, y value is the same. Okay, it's symmetric with respect to y-axis. Test intervals. So we're gonna count all the x value here, negative 2 to 0. That those three numbers will split the domain, the negative infinity and to positive infinity into 4 sub-intervals. First one is from negative infinity to negative 2. Second one, negative 2 to 0, 0 to 2, and 2 to positive infinity. Okay. So that's the test interval. Then next step, we come up with a table like this. We basically summarize what happened in the original function, in the first derivative, second derivative. Okay? And from negative infinity to negative 2. You can pick a test value. In this case, let's pick x equals to negative 3. Right? If you place into the first derivative is x equals to 20x over x squared minus 4 squared. As you can see, when x equals negative 3, the numerator is negative, the denominator is always positive. so the result will be negative, right? That's why it's negative. And for the second derivative, well, x equals -3, and the numerator is negative, and denominator is positive. This whole thing will be always negative. The numerator of the second derivative is always negative. Because -20 times a non-negative number, 3x squared plus 4 is always going to be greater or equal to 4. And make it non-negative, make it always negative. And the denominator, x squared, will be 9. 9 minus 4, 5. 5 cubed is 125, is positive. That's why second derivative is negative. So when first derivative is negative, that means it's decreasing. And then second derivative is negative, it's concave downward. Okay. And then x equals -2, that's first the original function, first derivative, and the second derivative. They're all undefined because all of them has a denominator which is x squared minus 4. When you plug in either -2 or 2, you always end up with a 0 as a denominator. So it's always undefined. The good thing is this is our very class now. And let's take a look at the second interval from -2 to 0. So you're going to pick a test value, -1. So as you can see, if you throw into the first derivative, right, the numerator will be -20. Denominator is always going to be positive. So -20 divided by a positive number is always going to be negative. Second derivative, the numerator is negative, and denominator is also negative because -1 squared becomes 1. 1 minus 4 is -3. -3 cubed is -27. So 2 negative turn into positive. Okay. So that indicates in this interval this part of graph is decreasing and concaving upward, right? First derivative being negative, that's decreasing interval, and second derivative being positive, that's concave upward. And x equals 0, we get an -2, that's the y-intercept. X equals 0, the first derivative equals 0. That means it is possible relative extremer. And if you look at the second derivative, x equals 0, numerator is negative always. Denominator is also negative. 2 negative turn into positive. So that tells us it's a relative minimum. Okay. And next interval is from 0 to 2. So you're going to pick test value. X equals 1. And plug into the first derivative. The numerator is positive. The denominator is positive. So it turned out to be positive. The second derivative, numerator is negative, and throwing the 1 into the denominator, you get -3 cubed, which is -27. So -2 negative turned into positive. So that means it's increasing and concave upward. In that particular interval, the graph of the function. X equals 2, that's vertical asymptote again. And the last interval is from 2 to positive infinity. So pick test value x equals 3 and plug into the first derivative. Then we're going to have a numerator which is 60, which is positive, right? Denominator is always positive. 2 positive turn into positive. So that means it's increasing graph. Second derivative, numerator is always negative. Denominator 3 squared is 9, 9 minus 4, 5, 5 cubed is 125, is positive. Negative over positive is negative. So that means it's concaving downward. Okay, so this is like for a complete analysis of the whole graph of function in details. And this is actually our graph. You can also get it from the graphing calculator or Maple. It's very easy to get this. As you can see, the graph actually will matches with the summary from the table. So from negative infinity to negative 2, that's 2. Those two, that x equals negative 2 and 2, those are the vertical asymptote. Horizontal asymptote, that's x equals to 2. Okay. And for negative infinity to negative 2, it's concaving downward and decreasing, right? That matches with the table. And from 0 to 2 is concaving upward and decreasing. From 0 to 2, that's concaving upward and increasing. The last part of graph from 2 to positive infinity is concaving downward and increasing. Okay, so using the calculus, you actually can get a lot of information about the graph of the function. It also guides you to graph the function in a lot more complete details. Okay, second part, we're going to take a look at the slash asymptotes. The slash asymptote occurs when we have a rational function. Slash asymptote only apply to rational function. And rational function will have numerator and denominator. When the degree of the numerator in the numerator is bigger than degree of denominator, then you're going to have a slash asymptote. Alright, that's what happened. And in order to find the slash asymptote, you got to do the long division. So let's take a look at this example. f of x equals to x squared minus 2x plus 4 over x minus 2. So when you apply the long division, so x squared minus 2x plus 4 divided by x minus 2. So you take two terms here, right? You use the leading term in your quotient divided by the leading term in your divisor, going to the leading term in your dividend. So we're going to do x squared divided by x, which gives us x. That means you're going to put x here. Then after that, you do subtract x times x is x squared, x times negative 2 is negative 2x. Okay? As you can see, these two are exactly the same, so you cancel that to end up with 0. And carry down the 4. So eventually, you just end up with 4 here, remainder of 4. So in this case, the slash asymptote will be y equals x. The quotient is the slash asymptote. So slash asymptote for this example is y equals to x. So no horizontal asymptote, but a slash asymptote. Because when the degree of numerator is bigger than the degree of denominator, that's no horizontal asymptote. But most likely you're going to have a slash asymptote in this case. So y equals x is the slant asymptote. When you graph it, this is our graph, and as you can see, the slant asymptote is right there. The vertical asymptote, you're setting x minus 2 equals 0, x equals 2 is the vertical asymptote. This is the vertical asymptote. That's slant asymptote. As you can see, these two asymptotes will split the region into 4 different regions. So the graph of function is located in these two regions. This region and this region. Okay. Note that the graph of f of x approaches the slant asymptote y equals to x as x approaches negative infinity or infinity.